The return first light. After solar conjunction, picture this. You're standing in the pre-dawn darkness, your breath visible in the cold November air, telescope pointed toward the eastern horizon. The sky's that deep indigo that comes just before sunrise, when stars still shine but the sun's approach is inevitable. And there, just 16 degrees from where our star will soon emerge, is a faint smudge of light that has travelled billions of years to reach this moment. 3i Atlas is back. If you're watching this video right now, do me a favour, hit that like button and subscribe to the channel. We're diving deep into the latest developments, and trust me, you won't want to miss what's coming. And hey, drop a comment telling me where you're listening from, what time it is there, and most importantly, have you tried to spot 3i Atlas yourself yet? I want to know if any of you have captured this interstellar wanderer with your own equipment. October the 31st, 2025, Halloween. While most of the world was focused on costumes and candy, astronomer Chicheng Jiang was doing something far more thrilling. He was bringing 3i Atlas back from the dead, so to speak. Not literally, of course, but after nearly a month of the comet being lost in the sun's overwhelming glare, Jiang successfully captured what is believed to be the first optical post-perihelion image of our interstellar visitor. Using the Lowell Observatory's Discovery Telescope in Arizona, a massive 4.3-meter instrument, he managed to photograph the comet when it was still dangerously close to the sun just above the horizon during morning twilight. Think about the precision required here for a moment. The comet was roughly 16 degrees away from the sun. To put that in perspective, if you hold your fist at arm's length against the sky, that's about 10 degrees. So we're talking about less than 2 fist widths from the blinding light of our star. The sky wasn't even properly dark. This was morning twilight, that delicate window when astronomical objects are still visible, but the sun is already beginning to paint the eastern sky with light. One wrong move, one miscalculation, and the telescope could have been pointed too close to the sun, potentially damaging sensitive equipment, or simply being overwhelmed by scattered sunlight. But Jiang didn't stop there. 2 days later, the telescope could have been pointed too close to the sun, potentially damaging sensitive equipment, or simply being overwhelmed by scattered sunlight. But Jiang didn't stop there. 2 days later, on November 2nd, he did something that sent ripples through the amateur astronomy community. He photographed 3i Atlas again, but this time using a small 6-inch telescope, a 152mm Ritchie-Chrétien reflector. This wasn't a multi-million-dollar observatory instrument. This was the kind of telescope that serious amateur astronomers own, the kind you can fit in your car, the kind that sits in backyards across the world, and it worked. The interstellar visitor was clearly visible, a fuzzy dot moving against the background stars. What this means is profound. For the first time since 3i Atlas vanished behind the sun in late September, everyday observers with modest equipment can from another star system. You don't need access to Hubble or Webb or some massive ground-based observatory. You need clear skies, a low eastern horizon, and a decent amateur telescope. Jiang himself told reporters that the comet won't look impressive, just a smudge, but it will be an increasingly visible smudge over the coming days. That sense of accessibility, that democratization of cosmic observation, is something special. This isn't just a scientific event anymore. It's something that belongs to anyone willing to wake up before dawn and point their telescope toward Virgo. The timing of this return is critical. 3i Atlas reached perihelion, its closest approach to the sun, on October 29. At that moment, it was approximately 203 million kilometers from our star, about 1.36 astronomical units. For comets, perihelion is the moment of maximum drama. The intense solar radiation heats the nucleus, causing volatile ices to sublimate directly from solid to gas, creating the characteristic coma and tail. It's when comets are typically at their brightest and most active. But here's the problem. From Earth's perspective, 3i Atlas was on the opposite side of the sun during this crucial period. We couldn't see it. Ground-based telescopes were completely blind to whatever was happening. This is where space-based observatories became absolutely essential. While Earth-bound astronomers waited in frustration, instruments like the Solar Terrestrial Relations Observatory, known as STEREO, the Solar and Heliospheric Observatory, called SOHO, and even the weather satellite GOES-19 kept their electronic eyes on the comet. These spacecraft, designed primarily to monitor the sun and space weather, found themselves tracking an interstellar visitor as it made its closest approach to our star. The data they collected during those invisible weeks has proven to be some of the most surprising and controversial information we've received about 3I Atlas so far. But we'll get to that shortly. The reappearance of 3I Atlas in early November marks the beginning of what astronomers are calling a critical observation window. Zhang noted that the comet is rapidly rising from the sun's position in our sky. Within a week of his first images, the comet would be 25, making it accessible to larger telescopes around the world. This increasing angular separation is crucial because it means more observation time per night, darker skies, and less interference from scattered sunlight. The comet is climbing higher in the pre-dawn sky with each passing day, moving northward from our perspective, making it progressively easier to observe from northern hemisphere locations. But let's talk about what observers are actually seeing now that 3I Atlas is back in view. The comet appears as a compact, slightly fuzzy white dot. There's a condensed central region, the coma surrounding the nucleus, and depending on the exposure length and telescope aperture, observers are reporting hints of a tail. Not the dramatic, sweeping tail of a great comet like Hale-Bopp, or even recent visitors like Comet Leonard. 3I Atlas is far more subtle. Its brightness is estimated to be around magnitude 9 to 10, which places it well beyond naked eye visibility, but easily within reach of binoculars and small telescopes under dark skies. For context, the faintest stars visible to the unaided eye under perfect conditions are around magnitude 6. Each magnitude step represents a change in brightness by a factor of about 2.5, so magnitude 9 is roughly 16 times fainter than what your eyes alone can detect. The visibility conditions are improving daily. On November 9th, the comet achieved an altitude of 10 degrees just before the start of dawn for observers at 40 degrees north latitude, roughly the latitude of cities like Denver or Philadelphia. The moon was in waning gibbous phase, which posed some challenges for visual observers due to the bright moonlight washing out faint objects. But by November 16th, the comet's altitude doubled to 20 degrees, and the moon became a thin crescent located just 4 degrees south of the comet. From November 16th through about December 2nd, the moon is essentially out of the picture, providing ideal dark sky conditions as 3I Atlas climbs the morning sky, moving through the constellation Virgo. There are some beautiful celestial alignments coming up for those tracking the comet. On November 18th and 19th, 3I Atlas passes 1.5 degrees south of Gamma Virginis, also known as Porrima, a second magnitude star that will serve as an excellent reference point for locating the comet. On November 22nd, it has a close encounter with the 13th magnitude galaxy NGC 4. Alignments are gifts for astrophotographers. Imagine capturing an interstellar comet from a planetary system billions of years old, passing in front of a galaxy containing hundreds of billions of stars all in a single frame. It's a cosmic perspective that puts our place in the universe into sharp focus. Zhang's images revealed something else important. The comet could still be brightening. The data suggests that 3I Atlas may not have reached its maximum brightness yet, even after perihelion. This is unusual but not unheard of. Some comets continue to brighten for days or even weeks after their closest solar approach as previously frozen volatiles deep within the nucleus finally get heated enough to sublimate. Whether this continued brightening is actually occurring with 3I Atlas requires more data, more observations from multiple locations and instruments. But the possibility is tantalizing because it suggests the comet might become even easier to observe than initially predicted. The Lowell Discovery Telescope's role in capturing these first images cannot be overstated. This is one of the few large telescopes in the world capable of pointing close enough to the horizon to observe objects shortly after they emerge from solar conjunction. Most major observatories have restrictions on how close they can point to the horizon due to atmospheric turbulence, light pollution from nearby cities, and the physical limitations of telescope mounts and domes. The Lowell telescope, situated at an elevation of 2,360 meters in northern Arizona, has relatively dark skies and a mount designed for flexibility. Zhang used this narrow window of opportunity, that brief period when the comet was above the horizon, but the sun was still far enough below it to allow imaging to secure these historic photographs. Think about the ephemeral nature of this opportunity. If Zhang had waited even a few more days, Other observatories might have beaten him to it. If he had tried a few days earlier, the comet might have been too close to the Sun to safely observe. This kind of astronomical work requires not just access to powerful equipment and clear skies, but also impeccable timing and a willingness to take calculated risks. Zhang reportedly uses a smaller 6-inch telescope to experiment and scout conditions before dedicating precious time on the larger Discovery telescope. Time on major research telescopes is incredibly competitive and scheduled months in advance. Every minute is valuable, every observation needs to count. His scouting work with amateur-grade equipment paid off spectacularly. Now that 3i Atlas is back in view, the scientific community is mobilizing. Observatories around the world are adding the comet to their observing schedules. Spectroscopes are being aimed at it to analyze the composition of gases in its coma. Photometric monitoring is tracking its brightness changes. Radio telescopes are listening for any emissions. Every piece of data collected now will help answer fundamental questions about this visitor from another star system. What is its nucleus made of? How does its composition compare to comets native to our solar system? What does its chemistry tell us about the molecular cloud where it formed billions of years ago? The European Space Agency's Jupiter Icy Moons Explorer, known as JUICE, is scheduled to observe 3i Atlas in November using multiple instruments. Although JUICE will be farther from the comet than the Mars orbiters were during the October flyby, it will see 3i Atlas just after perihelion, when the comet should be in its most active state. The data from JUICE won't be transmitted back to Earth until February, due to the spacecraft's distance and the rate at which it can send information. But when those observations arrive, they will provide yet another perspective on this mysterious object. There is something deeply moving about the return of 3i Atlas to our skies. For nearly a month it was hidden from us, doing whatever comets do when bathed in intense solar radiation with no witnesses from Earth watching. Now it's back, changed perhaps by its encounter with the Sun's heat, moving away from perihelion on its hyperbolic trajectory that will eventually carry it out of our solar system forever. This is not an object that will return in 76 years like Halley's Comet, or even in thousands of years like some of the long-period comets from the Oort cloud. 3i Atlas is here once, and only once. Every observation matters because there will never be another chance. Amateur astronomers around the world are setting their alarms for the pre-dawn hours, heading out into the cold November darkness with thermoses of coffee and star charts marked with the comet's predicted position. Some will succeed in capturing it, others will struggle with clouds, light pollution, or equipment issues. But they're all participating in a moment that will be remembered in astronomical history. They're all looking at photons left that distant comet, photons that travelled across the inner solar system, through Earth's atmosphere, and into their telescope optics. Those photons carry information from another star system, encoded in their wavelengths and intensities, waiting to be decoded. Zhang's images, both from the Discovery telescope and from his small amateur scope, are now circulating through astronomical communities online. Social media feeds filled with astrophotography are showcasing 3i Atlas, alongside images of galaxies, nebulae, and other comets. The interstellar visitor is becoming part of the regular observing schedule for dedicated comet watchers. Online forums are filling with reports. Captured it this morning at magnitude 9.5. Used an 8-inch Schmidt-Cassegrain, 30-second exposures, clearly visible in the stacked image. Attempted observation, but morning twilight was too bright. We'll try again tomorrow. This is citizen science at its finest. Professional astronomers with their million-dollar instruments, working alongside amateur observers with their backyard telescopes, all contributing pieces to the same cosmic puzzle. The democratization of astronomy, made possible by affordable imaging technology and the internet, means that someone in their driveway in suburban America might capture a detail or catch a sudden brightening that complements data from Hubble or Webb. The comet doesn't care whether it's being observed by a Nobel Prize winner or a high school student with a passion for the stars. It simply exists, moving through space, reflecting sunlight, and offering its secrets to anyone who looks carefully enough. As 3i Atlas climbs higher in the pre-dawn sky over the coming weeks, visibility will continue to improve. By mid-December, when the comet makes its closest approach to Earth at approximately 270 million kilometers, it will be high enough in the sky before dawn to allow for extended observation sessions. This December approach represents the final major milestone in our opportunity to study this object before it heads toward its March 2026 flyby of Jupiter and then departs our solar system permanently. The return of 3I Atlas after its solar conjunction is more than just an astronomical event. It's a reminder that the universe operates on its own schedule, indifferent to our desire to observe. The comet disappeared behind the Sun because orbital mechanics dictated it would. It reappeared when geometry allowed it, not a moment sooner. And now, for a brief window measured in weeks, we have the chance to point our instruments skyward and gather whatever information we can before this visitor from the depths of interstellar space continues its eternal journey through the galaxy. The fact that we can participate in this moment, whether through professional research or amateur observation, is one of the great privileges of living in an age where the cosmos is accessible to anyone with curiosity and a willingness to look up. Kim Kardashian to Congress. How 3I Atlas went viral. Something extraordinary happened in the last week of October 2025. An interstellar comet became the subject of tweets from reality television stars, demands from members of Congress, and heated debate from members of Congress, and heated debates across social media platforms worldwide. 3I Atlas transcended the boundaries of astronomical journals and science news websites to become a genuine cultural phenomenon. The question is, how did a faint speck of light in the morning sky capture the attention of millions of people who have never looked through a telescope? October 31st. Kim Kardashian posted on X, formerly known as Twitter. Wait, what's the T on 3I Atlas? The tweet was simple, casual, using the kind of language her hundreds of millions of followers understand. Within hours, it had been viewed millions of times. NASA's acting administrator Sean Duffy responded directly. NASA's observations show that this is the third interstellar comet to pass through our solar system. No aliens, no threat to life here on Earth. A straightforward answer from the head of the space agency to one of the most famous people on the planet, all playing out in public view on social media. But Kardashian's interest wasn't random curiosity. The conversation around 3I Atlas had been building for weeks in corners of the internet, where conspiracy theories flourish alongside genuine scientific discussion. YouTube channels dedicated to unexplained phenomena had been churning out videos with increasingly dramatic titles. Forums on Reddit were filling with speculation. And perhaps most concerningly, deepfake videos had begun circulating, featuring fabricated footage of respected scientists like physicist Brian Cox, apparently discussing alien origins for the comet. These weren't crude manipulations. They were sophisticated enough to fool casual viewers, using artificial intelligence to generate realistic voice patterns and facial movements. Brian Cox himself addressed the deepfakes publicly, expressing concern not just about the misuse of his image, but about the broader implications. Doesn't matter so much if it's nonsense about a comet, he tweeted, but in other areas of science and certainly politics it's clearly important. YouTube eventually removed several prominent accounts responsible for the deepfake videos, but the damage was done. The narrative that 3I Atlas might be something more than a natural comet had escaped the confines of fringe websites and entered mainstream consciousness. Enter Avi Loeb. The Harvard astrophysicist has become perhaps the most controversial figure in the 3I Atlas story, and his media appearances in late October and early November threw gasoline on an already burning fire. On October 30th, Loeb appeared on Joe Rogan's podcast, one of the most listened to shows in the world, with an audience measured in tens of millions. The conversation ranged across multiple topics, but when it turned to 3I Atlas, Loeb didn't hold back. He criticised NASA for what he called a lack of transparency regarding crucial observational data. The specific issue Loeb raised involved images from the HiRISE camera aboard the Mars Reconnaissance Orbiter. These images were taken on October 2nd and 3rd when 3I Atlas passed within 30 million kilometres of Mars. According to Loeb, the HiRISE camera achieved a spatial resolution of 30 kilometres per pixel, approximately 3 times better than the best publicly available Hubble images taken in July. More importantly, these images offered a sideways perspective on the comet, valuable for understanding the geometry of material being ejected from its surface. But as of Loeb's appearance on the Rogan podcast, NASA had not released these images publicly. 4 weeks had passed since they were captured. Loeb's explanation for the delay was blunt. When Rogan asked if the holdup might indicate something unusual in the images, something NASA wanted to hide, Loeb dismissed the conspiracy angle with characteristic directness. The delay is probably not a sign of extraterrestrial intelligence, but rather of terrestrial stupidity. He attributed the issue to the government shutdown that began on October 1st, arguing that science was being held hostage to political dysfunction. "We should not hold science hostage to the shutdown politics of the day," he stated. The scientific community would have greatly benefited from the dissemination of this time-sensitive data as astronomers plan follow-up observations in the coming months. The Joe Rogan appearance did exactly what such appearances typically do. It amplified Loeb's message to an audience far beyond academic circles. Rogan suggested that Loeb contact NASA Administrator Sean Duffy directly. Loeb took that advice, but he also reached out to someone with potentially more leverage, Congresswoman Anna Paulina Luna. Representative Luna, a Republican from Florida, has a history of interest in unexplained aerial phenomena and unconventional science, questioned witnesses during congressional hearings on UFOs, and has advocated for greater transparency in government-held scientific data. When Loeb contacted her regarding 3I Atlas, she responded swiftly. On October 31st, the same day Kim Kardashian tweeted her question about the comet, Luna sent a formal letter to acting NASA Administrator Sean Duffy. The letter was remarkably direct. Luna requested the immediate release of the high-rise images from the Mars Reconnaissance Orbiter. She specifically noted that these images possess a spatial resolution of 30 kilometers per pixel, approximately 3 times better than the spatial resolution achieved in the best publicly available image from the Hubble Space Telescope taken on July 21, 2025. The letter emphasized that this information is of great importance to advancing our understanding of interstellar visitors and their interaction with our solar system. But Luna's letter went further. She also requested any supplementary data from Mars missions that may have detected unusual activity near Mars during 3I Atlas's closest approach. This phrasing raised eyebrows. What kind of unusual activity? The letter didn't specify, leaving room for interpretation and, inevitably, speculation. Luna also encouraged NASA to fund additional observations of 3I Atlas using the Juno spacecraft, currently orbiting Jupiter, utilizing all available instruments including radio sensors. On November 3rd, Luna followed up with another tweet, this time tagging it directly. "Can you please see letter below? We would like to see images of 3I Atlas." She attached the full text of her October 31st letter. The pressure was now public, visible, and coming from an elected representative with a platform. The response from NASA was measured. Administrator Duffy's reply to Kim Kardashian represented the agency's official position. 3I Atlas is the third known interstellar comet. It exhibits no signs of being anything other than a natural object. It poses no threat to Earth. This is a scientific opportunity, not a crisis. NASA lead scientist Tom Statler went further in comments to media outlets, stating that 3I Atlas very, very strongly resembles known comets, and dismissing speculation about artificial origins. But these reassurances did little to quell the conversation. Loeb fired back at Statler's comments in interviews with outlets like LadBible. The statement from NASA, or anyone else, that conclusively says something and wants other opinions not to be heard is really counterproductive, because the public deserves to hear different scientific perspectives. He argued that declaring the matter settled without releasing all available data was antithetical to the scientific method. The situation escalated further when journalist Christina Gomez published a detailed analysis revealing that Luna had actually sent 2 letters to NASA about 3I Atlas. The first, dated July 31st, proposed redirecting the Juno spacecraft to intercept the comet, citing Loeb's analysis that a specific thrust maneuver on September 14th could position Juno for observations during 3I Atlas's March 2026 flyby of Jupiter. The estimated cost was $15 million for a 6-month mission extension. That first letter went unanswered. The second letter in October took a dramatically different approach, demanding release of data NASA had already collected rather than proposing new observations. This shift suggested that Luna and her staff realized the agency had been observing 3I Atlas extensively, but was withholding findings. The controversy drew in other high-profile figures. Elon Musk, who has his own complicated relationship with space agencies, given his role leading SpaceX, made cryptic comments about 3i Atlas in various forums. Tech influencers and science communicators found themselves fielding questions from audiences who suddenly cared deeply about cometary orbital mechanics and spectroscopic analysis. The comet became a trending topic not just once but repeatedly as each new development emerged. What made the 3i Atlas saga particularly potent was how it combined several elements that resonate in contemporary culture. There's the distrust of government institutions and demands for transparency. There's the tension between establishment science and contrarian voices like Loeb. There's the accessibility of the story, a visitor from another star system passing through our cosmic neighbourhood. And there's the genuine mystery, the unanswered questions about the comet's anomalous behaviour that even mainstream scientists acknowledge. The deepfake issue added another layer. In an era where artificial intelligence can fabricate convincing videos of anyone saying anything, the 3i Atlas story became a case study in how misinformation spreads. The fake Brian Cox videos weren't created by state actors or sophisticated propaganda operations. They were made by individuals seeking views and engagement, monetizing conspiracy theories through YouTube's advertising system. The fact that YouTube eventually took action demonstrated both the problem and the inadequacy of platform moderation when content can be created and uploaded faster than it can be reviewed. Social media algorithms amplified everything. Posts about 3i Atlas that generated engagement, whether through genuine scientific interest or conspiracy speculation, were promoted to more users. The more dramatic the claim, the more likely it was to be shared. Neutral scientific updates competed for attention against headlines suggesting alien motherships or NASA cover-ups. In this environment, a congresswoman demanding data release and a Harvard professor questioning official narratives provided fuel for every interpretation. The scientific community found itself in an uncomfortable position. Researchers who had spent months carefully observing 3i Atlas, writing papers, and analysing data suddenly had to contend with their work being discussed by millions of people, many of whom had no background in astronomy. Some welcomed the attention, seeing it as an opportunity to engage public interest in science. Others worried that the signal-to-noise ratio had become impossible to manage, that legitimate questions were being drowned out by sensational. Loeb himself became a lightning rod. His critics, and there are many in the astronomical community, accused him of seeking publicity and promoting fringe theories to sell books and secure funding for his Galileo project, which searches for evidence of extraterrestrial technology. His supporters argued he was asking questions that needed asking and challenging an establishment that had grown too comfortable dismissing anomalies. The truth, as often happens, likely existed somewhere in the nuanced space between these extremes. But here's what the viral moment accomplished, intended or not. It forced NASA to engage with public questions about 3i Atlas at a level that wouldn't have happened otherwise. It brought attention to the importance of timely data release in astronomy, where observation windows can be fleeting. It demonstrated that people care about interstellar visitors, even faint ones requiring telescopes to see. And it created a cultural moment where a comet, a chunk of ice and rock from another star system, became part of the conversation happening around dinner tables and water coolers. The high-res images remain unreleased as of early November. NASA has not provided a specific timeline for their publication. The scientific papers analysing 3i Atlas continue to appear on preprint servers and in journals. The comet continues moving through space, indifferent to the human drama playing out in its wake. And the question of transparency in science, particularly when dealing with objects of intense public interest, remains unresolved. Kim Kardashian's tweet might seem like a trivial footnote in this story, but it represents something important. When one of the most followed people on social media asks about an astronomical object, it signals that the object has broken through into mass consciousness. Whether that's good or bad for science depends on your perspective, but it's undeniably powerful. 3i Atlas went from being a specialised interest for comet researchers to being something discussed by hundreds of millions of people worldwide. That kind of attention brings both opportunities and challenges, and how the scientific community navigates this moment may influence public engagement with astronomy for years to come. Amateur visibility. Small telescopes capture the interstellar visitor. There's something profoundly democratic about the night sky. A photon that travelled from 3i Atlas doesn't care whether it lands on the mirror of the Hubble Space Telescope or the lens of a 6-inch reflector in someone's backyard. The physics is identical. The information encoded in that photon's wavelength and intensity is the same. And in early November 2025, amateur astronomers around the world realised they had joined an exclusive club. They could observe an interstellar object with their own equipment. The moment Qicheng Zhang published his November 2nd image, taken with a 152mm telescope, the amateur astronomy community erupted with activity. Forums that typically discuss equipment reviews and astrophotography techniques suddenly filled with threads about 3i Atlas. Is it really visible in my 8-inch Schmidt Cassegrain? What exposure time do I need? Can I see it from my suburban backyard, or do I need dark skies? The questions poured in from observers at every experience level. Within 48 hours, confirmation images started appearing. An observer in Arizona using a Celestron 8-inch telescope reported capturing the comet clearly in a stack of 20 30-second exposures. Someone in New Mexico with a 10-inch Dobsonian reflector posted a sketch made at the eyepiece, showing the comet as a diffuse circular glow with a faint tail extension toward the southwest. A photographer in California stacked 200 frames taken with a telephoto lens mounted on a tracking mount, producing an image that showed not just 3i Atlas but several background galaxies in the same field of view. The accessibility of 3i Atlas to amateur equipment represents something relatively rare in modern astronomy. Most objects that generate significant scientific interest are far too faint for backyard telescopes. Exoplanets require space telescopes and sophisticated analysis techniques. Distant galaxies might be photographable by dedicated amateurs, but observing them contributes little to professional research. Asteroid discoveries have been largely automated by survey programs that scan the sky more thoroughly than any individual could. But 3i Atlas occupies a sweet spot. It's bright enough to capture with moderate amateur equipment, yet every observation contributes meaningful data. Why does amateur data matter for an object being studied by the world's most powerful telescopes? Because professional observatories have limited time and can't watch the comet continuously. A sudden outburst, a brightness fluctuation, a change in coma structure, these events, could happen between scheduled professional observations. Amateur astronomers, especially those who are retired or have flexible schedules, can monitor targets regularly. They can catch changes that might otherwise be missed. And with 3i Atlas approaching its December closest approach to Earth, continuous monitoring becomes scientifically valuable. Consider the global distribution of amateur observers. When sunset arrives in Europe, it's already night in Asia, and still afternoon in the Americas. This provides nearly continuous coverage of the sky. 3i Atlas rises in the pre-dawn sky, which means observers in different time zones can watch it at different hours, creating an observational relay race that follows the rotation of Earth. Someone in Japan photographs the comet before dawn, then an observer in Europe picks it up a few hours later as dawn breaks there, followed by North American observers continuing the coverage. Professional observatories can't match this geographic diversity and temporal coverage. The technical requirements for observing 3i Atlas are modest by astrophotography standards. The comet is currently around magnitude 9 to 10, which means it's visible in binoculars under dark skies, though it appears very faint and requires knowing exactly where to look. A 4-inch telescope makes it readily visible as a fuzzy patch distinct from background stars. A 6 to 8-inch telescope, the workhorses of amateur astronomy, show the comet clearly with obvious coma structure. Larger amateur instruments 10 inches and up can begin to reveal tail details and track subtle changes in brightness. The imaging process requires patience but not exotic equipment. A tracking mount, essential for any deep sky astrophotography, keeps the telescope pointed at the comet as Earth rotates. A camera, either a dedicated astronomy camera or a modified digital single-lens reflex, captures individual frames. Most observers use exposures between 30 seconds and 2 minutes, balancing the need to gather light against the comet's motion across the sky. Then comes stacking, combining dozens or hundreds of frames to reduce noise and enhance faint details. Software like Deep Sky Stacker or PixInsight handles this processing, transforming a collection of noisy individual images into a clean final result. But here's where 3i Atlas presents a unique challenge. Unlike photographing a stationary galaxy or nebula, The comet is moving relatively quickly against the background stars. This means that stacking software needs to track the comet's motion, not the stars. Some programs have built-in comet stacking modes. Others require manual alignment using the comet itself as the reference point. The result is that stars appear as streaks while the comet remains sharp, the opposite of what happens when tracking stars while a comet drifts through the field. Several amateur observers have taken this challenge and turned it into art. Images showing 3-eye Atlas as a crisp point with radiating star trails around it create a visual representation of the comet's motion through our solar system. One photographer created a time-lapse animation from frames taken over 3 hours, showing the comet's movement against the stellar background in real time. These aren't just pretty pictures, they're demonstrations of orbital mechanics made visible. The community aspect of amateur observation has been remarkable. The 3-eye Atlas TV account on X, run by enthusiasts tracking every development related to the comet, has become a clearinghouse for amateur images. Observers tag their photos, share acquisition details, and provide feedback on each other's work. There's no competition here, no sense of trying to get the best image. Instead, there's collaboration. Someone who successfully imaged the comet shares their exact settings, helping others who struggled with clouds or equipment issues. Tips are exchanged on dealing with light pollution, managing dew formation on optics during cold pre-dawn sessions, and processing techniques for enhancing faint details. For many amateur astronomers, 3-eye Atlas represents their first opportunity to observe an interstellar object. 1-eye Oumuamua, the first confirmed interstellar visitor discovered in 2017, was far too faint for amateur equipment by the time its interstellar nature was confirmed. 2-eye Borisov, discovered in 2019, was more accommodating, reaching magnitude 15 at its brightest, making it accessible to experienced amateurs with larger telescopes and imaging equipment. But 3-eye Atlas is brighter than Borisov was, making it visible to a wider range of observers. This accessibility has educational implications. High school astronomy clubs are organising pre-dawn observing sessions, letting students see an actual visitor from another star system through their school's telescope. Universities are incorporating 3-eye Atlas observations into undergraduate astronomy labs, teaching students about orbital mechanics, spectroscopy, and the scientific method while observing a genuine research target. Planetariums and science centres are hosting public viewing events, though the pre-dawn timing makes these challenging to schedule. The observing conditions in November and December are progressively improving for Northern Hemisphere observers. The comet's altitude above the horizon increases each morning, providing darker backgrounds and more observation time before twilight brightens the sky. By mid-November, 3-eye Atlas rises about 2 hours before the sun at mid-northern latitudes, giving observers a comfortable window. Cold November mornings bring excellent atmospheric transparency, the bane of summer observers who deal with haze and humidity. Winter air, though uncomfortable for the astronomer, provides some of the clearest skies of the year. Southern Hemisphere observers face different conditions. The comet's trajectory and current position favour northern viewers, though it remains visible from southern latitudes with some difficulty. Observers in Australia and South America report needing clear horizons and careful timing to catch the comet low in the sky before sunrise. This geographic bias in visibility has concentrated observations in North America, Europe, and Asia, though dedicated Southern Hemisphere astronomers are still contributing data. Equipment reviews have taken on new relevance as observers seek to optimize their setups for cometary observation. Which eyepieces provide the best views of low surface brightness objects? What camera sensors are most sensitive to the wavelengths where cometary emissions occur? How do different telescope designs, refractors versus reflectors, affect contrast when observing against twilight skies? These technical discussions, usually abstract, now have a concrete application. The answers matter because observers want to see 3-eye Atlas as clearly as possible. Some amateurs have gone beyond simple imaging to attempt more sophisticated observations. Spectroscopy, once the exclusive domain of professional astronomy, has become accessible to advanced amateurs with specialized equipment. A handful of observers have obtained low-resolution spectra of 3-eye Atlas, identifying emission lines from carbon compounds in the coma. These amateur spectra won't replace professional observations from instruments like the James Webb Space Telescope, but they demonstrate what's possible with dedication and modest equipment. The data gets shared online, added to the collective understanding of the comet's composition. Photometry, precise brightness measurements, is another area where amateurs contribute. By carefully measuring the comet's magnitude over multiple nights, observers can track brightness changes that might indicate rotational variations in the nucleus or changes in outgassing activity. Professional photometry is more precise, but amateur observations provide temporal coverage that would be impossible otherwise. A network of amateur photometrists can monitor 3i Atlas every clear night from locations around the world, creating a continuous light curve that captures short-term variability. The experience of observing 3i Atlas has been described by many amateurs as humbling and awe-inspiring in equal measure. One observer posted about setting up their telescope at 4:30 in the morning, hands numb from cold, watching their breath form clouds in the beam of their red headlamp. When the comet finally appeared in the eyepiece, just as predicted by the ephemeris, they reported feeling a connection across billions of years and incomprehensible distances. That fuzzy patch of light was matter from another star system, older than Earth, that had travelled through the void to appear in their telescope on this particular morning. Another observer described the challenge of explaining to neighbours why someone would be outside in freezing temperatures before dawn, pointing a tube at the sky. After showing them the comet through the eyepiece and explaining what they were seeing, the neighbour stood silently for a moment before saying, "We're really not alone, are we?" That sense of perspective, of understanding Earth as one small world in a galaxy filled with planetary systems, comes through powerfully when viewing an interstellar visitor. The coming weeks represent the peak opportunity for amateur observation. As 3i Atlas approaches its December 19th closest approach to Earth, it will be well positioned in the morning sky for Northern Hemisphere observers. The Moon will be moving into new phase in mid-December, providing dark skies. And if the comet continues brightening as some data suggests it might, it could become even more accessible to smaller telescopes and possibly strong binoculars. This is the moment amateur astronomers have been waiting for since the comet's discovery in July. But beyond the technical aspects and the scientific contributions, there's something profound about the democratization of this cosmic event. 3i Atlas isn't hidden behind proprietary data or accessible only to those with access to major observatories. It's there for anyone willing to wake up early, point their telescope east, and look. That inclusivity, that openness of the universe to observation by anyone curious enough to try, is what keeps amateur astronomy thriving in an age of automated surveys and space telescopes. The comet doesn't check credentials before reflecting sunlight into your optics. It simply exists, visible to all, a reminder that the cosmos belongs to everyone who looks up. The brightening mystery, why 3i Atlas defied predictions. Something unexpected happened while 3i Atlas was hidden behind the sun. The comet got bright. Not just bright in the way comets normally do as they approach perihelion, but bright in a way that exceeded every prediction, every model, every expectation based on decades of cometary science. And astronomers watching the data come in from space-based observatories found themselves facing a puzzle with no clear answer. The story begins with instruments that weren't designed to study comets at all. The Solar Terrestrial Relations Observatory, STEREO, consists of twin spacecraft monitoring the sun and space weather. The Solar and Heliospheric Observatory, SOHO, watches for coronal mass ejections and solar activity. The GOES-19 weather satellite tracks conditions relevant to Earth's atmosphere and magnetic field. These instruments observe the sun continuously, and when 3i Atlas passed through their fields of view during late September and October, they captured something remarkable. Qicheng Zhang from Lowell Observatory and Carl Battams from the US Naval Research Laboratory analysed the data and published their findings in a preprint paper, posted to the Arciv server. What they found was dramatic. 3i Atlas brightened rapidly during its approach to perihelion, with a rate that far exceeded what's observed in typical Oort cloud comets at similar distances from the Sun. The brightness scaled inversely with distance from the Sun to the power of negative 7.5 plus or minus 1. For context, most comets show an inverse relationship to the power of negative 2 to negative 4. 7.5 is extraordinary. The paper's language is carefully measured, as scientific papers must be, but the implications are clear. The reason for 3i Atlas's rapid brightening which far exceeds the brightening rate of most Oort cloud comets at similar radial distances, remains unclear. That single sentence, buried in technical analysis and observational data, represents one of the central mysteries of this interstellar visitor. Let's break down what this rapid brightening means. When a comet approaches the Sun, solar radiation heats its surface, causing volatile ices to sublimate directly from solid to gas without passing through a liquid phase. This outgassing creates the coma, the fuzzy atmosphere around the nucleus, and often produces tails of gas and dust that point away from the Sun. The closer the comet gets, and typically, the brighter the comet becomes. This is expected behaviour, understood through decades of observation and modelling, but 3I Atlas brightened faster than it should have. The rate at which its luminosity increased suggested something unusual was happening. Either the comet's composition is dramatically different from typical solar system comets, or something about its structure or behaviour is atypical, or both. Zhang and Battams propose several potential explanations in their paper, each with intriguing implications. The first possibility involves the speed at which 3I Atlas is approaching the Sun. The comet is moving fast, approximately 137,000 miles per hour, significantly faster than most comets from the Oort cloud, and faster than either of the previous interstellar visitors. This high velocity means that the heating from solar radiation occurs more rapidly, potentially triggering outgassing processes at a different rate than slower-moving objects experience. It's possible that the physics of cometary activation changes when the object is moving at interstellar velocities through the inner solar system. The second possibility relates to the comet's internal composition. 3I Atlas might have oddities in its nucleus properties, aspects of composition, shape, or structure that it acquired either in its home star system billions of years ago or during its long journey through interstellar space. If the ratio of different volatile ices differs from solar system comets, the outgassing behaviour could be fundamentally different. Imagine a comet with an unusually high proportion of carbon dioxide relative to water ice. Dioxide sublimes at much lower temperatures than water ice, meaning it begins outgassing farther from the Sun. This could create a cooling effect that initially suppresses water ice sublimation, then releases it suddenly once the comet gets hot enough, causing a brightness surge. In fact, observations from the James Webb Space Telescope and other instruments have confirmed that 3I Atlas is unusually rich in carbon dioxide compared to most known solar system comets. The Webb observations from August 6th showed the comet's bright, condensed coma and revealed that carbon dioxide dominated the gas emissions, with water and carbon monoxide also present but in different proportions than typically observed. This chemical signature points toward a planetary system environment different from our own, a molecular cloud with different abundances of elements and compounds. The third element of the brightening mystery involves colour changes. Zhang and Battams noted that colour photometry showed 3I Atlas to be distinctly bluer than the Sun near perihelion. This observation is genuinely surprising. Dust typically reddens reflected sunlight, similar to how Earth's atmosphere makes sunsets appear red. The surface of 3I Atlas, being much colder than the Sun's photosphere, should also produce reddish reflected light. Yet the comet appeared blue. Blue colouring in comets usually indicates gas emissions rather than reflected sunlight. Specific molecules, when excited by solar radiation, emit light at characteristic wavelengths, many of which fall in the blue portion of the spectrum. Ionized carbon monoxide, for instance, produces blue emissions. The observation that 3I Atlas appeared blue suggests that gas emissions contributed substantially to the comet's visible brightness near perihelion, not just reflected sunlight from dust. This aligns with the rapid brightening, gas production increasing dramatically, creates both the brightness surge and the blue colour. But here's where things get interesting from a more speculative standpoint. Avi Loeb, never one to shy away from unconventional interpretations, published an analysis noting that the blue colour could potentially be explained by artificial sources. A hot engine or a source of artificial light would produce blue emissions. He immediately clarified that natural processes could also explain the colour, particularly ionized molecules in the coma, but the mention of artificial possibilities generated significant attention. Loeb has consistently maintained that 3I Atlas ranks high on his scale for objects deserving serious investigation for potential technological origins, and the brightening anomaly plus blue colour add to his list of unexplained features. The scientific community's response to the brightening data has been mixed. Some researchers see it as evidence that interstellar comets may, have systematically different compositions than solar system comets, reflecting different formation environments around other stars. Each planetary system forms in a unique molecular cloud with specific elemental abundances. Our solar system's comets tell us about the cloud from which our Sun formed 4.6 billion years ago. 3I Atlas, potentially 7 to 11 billion years old, formed in a completely different environment, possibly around a star that has long since died. Its chemistry should differ. Other scientists caution against overinterpreting preliminary data. Space-based coronagraphs, while invaluable for observing objects near the Sun, aren't optimized for precise photometry of comets. The brightness measurements have uncertainties. The models used to predict cometary brightening are based primarily on Oort cloud comets, which themselves show enormous variability in behavior. Perhaps 3I Atlas falls within the natural range of cometary behavior, just at an extreme end. More data is needed before conclusions can be drawn firmly. The paper by Zhang and Battams acknowledges this uncertainty explicitly. Without an established physical explanation, the outlook for 3I Atlas's post-perihelion behavior remains uncertain, and a plateau in brightness, or even a brief continuation of its pre-perihelion brightening, appears as plausible as rapid fading past perihelion. In other words, they don't know what will happen next. The comet could maintain its brightness, continue brightening for a time, or fade rapidly now that it's moving away from the Sun. Each outcome would provide clues about what drove the anomalous brightening. This is where the current observational campaign becomes critical. Ground-based telescopes, now that 3I Atlas has emerged from behind the Sun, can track its brightness evolution with much greater precision than space-based solar observatories could during perihelion. If the comet continues showing unusual brightness behavior, it strengthens the case that something genuinely anomalous is occurring. If it settles into more typical cometary behavior, it suggests the rapid brightening was a temporary phase, perhaps related to specific ices sublimating at perihelion. One hypothesis that has gained traction involves the concept of delayed water ice activation. Carbon dioxide sublimes easily, beginning at distances of several astronomical units from the Sun. This sublimation cools the surface through evaporative cooling, similar to how sweating cools human skin. The cooling effect can actually suppress water ice sublimation, keeping it frozen even as the comet approaches the Sun. But eventually the solar heating overwhelms the cooling effect. When water ice suddenly begins sublimating in large quantities, the comet brightens dramatically. This could explain both the rapid brightening and the unexpected timing. Supporting this hypothesis is data from the Sphere-X spacecraft, which observed 3I Atlas in August. Those observations showed the carbon dioxide plume extending out to approximately 348,000 kilometers from the nucleus, an enormous distance that indicates vigorous carbon dioxide outgassing. If this gas was indeed providing a cooling effect, it might have kept water ice dormant until perihelion, when the heating became intense enough to trigger widespread water ice sublimation. The detection of water by NASA's Neil Gehrels Swift Observatory adds another piece to this puzzle. The Swift telescope, pointing at 3I Atlas, detected hydroxyl gas, a chemical fingerprint of water. Hydroxyl is produced when water molecules are broken apart by solar radiation. This detection confirms that water is present and active in the comet's coma. The question is whether water activation increased suddenly near perihelion, contributing to the brightness surge, or whether it's been steady throughout the comet's approach. Spectroscopic observations in the coming weeks will help answer these questions. By analysing the specific wavelengths of light coming from 3I Atlas, astronomers can identify which molecules are present in the coma and in what quantities. If water emissions increase dramatically compared to earlier observations, it supports the delayed activation hypothesis. If carbon dioxide remains dominant even now, it suggests a different explanation for the brightening. The brightening mystery also has implications for mass loss. Loeb calculated that if the rapid brightening resulted from massive outgassing, 3I Atlas might have lost a significant fraction of its mass during perihelion, potentially as much as 10%. Such dramatic mass loss should be detectable as a large debris cloud around the comet in the coming months. European Space Agency's JUICE spacecraft, scheduled to observe 3I Atlas in November, might be the first to detect this debris field if it exists. The observations won't reach Earth until February due to transmission delays, but they will provide crucial data about the comet's post-perihelion state. If 3I Atlas did lose 10% of its mass, That would represent the evaporation of a surface layer averaging 4 centimeters thick across the entire nucleus. For an object estimated to be between 440 meters and 5.6 kilometers in diameter, that's a substantial amount of material. The absence of such a debris field would suggest that the brightening was not primarily due to standard cometary outgassing, opening the door to more exotic explanations. The brightening mystery represents science in action, confronting unexpected observations and working to develop explanations. Every hypothesis generates predictions that can be tested with future observations. The scientific method doesn't require that we immediately understand everything we see. It requires that we acknowledge what we don't understand and work systematically to figure it out. 3i Atlas has given astronomers something genuinely puzzling to work on, and the resolution of this mystery, whatever it turns out to be, will advance our understanding of comets, interstellar objects, or perhaps both. December. Approach. Final opportunity before Jupiter and beyond. December 19th, 2025. Mark that date. On that day, 3i Atlas will make its closest approach to Earth, passing at a distance of approximately 269 million kilometers, about 1.8 astronomical units. This represents the final major observation window before the comet continues its journey toward Jupiter and then leaves our solar system forever. Every telescope that can be pointed at the comet will be watching. Every instrument capable of gathering data will be active. This is it, the last chance. But the story doesn't start on December 19th. It's happening right now, building through November and into early December as the geometry becomes increasingly favourable. The comet is climbing higher in the pre-dawn sky with each passing morning. Its altitude above the eastern horizon for Northern Hemisphere observers increases daily, providing darker backgrounds and longer observation windows before twilight washes out the sky. By early December, 3i Atlas will be well placed for extended imaging sessions, rising several hours before the sun. The moon's phases are cooperating beautifully. The new moon on December 1st provides ideal dark sky conditions, just as the comet reaches optimal altitude. Through the first 2 weeks of December, the moon remains either new or in thin crescent phase, rising shortly before the sun and contributing minimal light pollution to the pre-dawn sky. Observers won't face the challenge of a bright moon overwhelming the comet's faint glow. Nature has provided perfect viewing conditions for the climax of this celestial visit. Professional observatories are coordinating their efforts to maximize data collection during this window. The Hubble Space Telescope, which captured detailed images of 3i Atlas back in July when the comet was 277 million miles from Earth, is scheduled for additional observations in December. At closer range, and with the comet potentially still active from its recent perihelion passage, Hubble should be able to resolve the coma structure in unprecedented detail, possibly revealing the nucleus itself if the surrounding dust has thinned sufficiently. The James Webb Space Telescope, with its near-infrared capabilities, will continue spectroscopic observations to track how the comet's composition and activity evolve as it moves away from the Sun. Webb's earlier observations in August detected carbon dioxide, water and carbon monoxide in the coma. Follow-up observations in December will show whether these abundances have changed, whether new molecules have appeared as different ices sublimate, and whether the unusual carbon dioxide dominance persists or shifts toward more typical cometary chemistry. Ground-based observatories around the world are dedicating time to 3i Atlas. The Gemini telescopes, both north in Hawaii and south in Chile, have scheduled observations using multiple instruments. The Keck Observatory in Hawaii, which provided earlier spectroscopic data showing the puzzling nickel emissions without corresponding iron, will continue monitoring the comet's chemical composition. The Very Large Telescope in Chile, with its powerful spectroscopic capabilities, will analyze the coma's structure and composition across multiple wavelengths simultaneously. Radio telescopes are listening. While 3i Atlas is not a radio source itself, radio observations can detect specific molecules in the coma through their characteristic emission lines. The Atacama Large Millimeter Array, ALMA, with its extraordinary sensitivity, might detect rare molecules that optical telescopes cannot observe. These measurements would provide insights into the comet's chemical inventory, revealing compounds that formed in its home star system billions of years ago and have been preserved frozen ever since. The December approach also represents a critical test for several hypotheses about 3i Atlas. If the comet lost massive amounts of material during perihelion, as some models suggest based on the rapid brightening, December observations should reveal a large debris cloud. This cloud would scatter sunlight, appearing as an extended halo around the nucleus. The size and structure of this debris field would provide direct evidence of how much material was ejected and how violently it occurred. Conversely, if no substantial debris cloud is detected, it would suggest that the brightening mechanism was not primarily standard cometary outgassing, demanding alternative explanations. The question of non-gravitational acceleration becomes testable during the December approach. David Farnocchia from NASA's Jet Propulsion Laboratory reported detecting non-gravitational acceleration at perihelion, with both radial and tangential components. This acceleration, if caused by outgassing, should produce a predictable trajectory deviation. Precise astrometric measurements in December, tracking the comet's exact position against background stars, will show whether the trajectory matches predictions based on the measured acceleration, or whether additional forces are at work. Any discrepancy would be significant. For amateur astronomers, December represents the culmination of months of anticipation. The comet will be at its brightest apparent magnitude since discovery, potentially reaching magnitude 8 or even brighter if post-perihelion activity continues. At magnitude 8, 3i Atlas becomes visible in binoculars under reasonably dark skies, not just requiring telescopes. For casual observers willing to wake before dawn and follow a star chart to locate the comet, this might be their only chance to see an interstellar object with their own eyes, or at least with minimal optical aid. The visibility window extends through late December and into early January 2026, though the comet will be fading by then as it moves farther from both the Sun and Earth. Professional interest will remain high, even as the comet dims, because every additional data point helps constrain models of its composition and behaviour. But for most observers, December is the moment, the comet at its closest, brightest, and most accessible. After December, 3i Atlas continues on its hyperbolic trajectory out of the inner solar system. The next major encounter is with Jupiter on March 16, 2026. The comet will pass approximately 53 million kilometres from the giant planet, close enough that Jupiter's intense magnetic field and radiation belts might affect the comet's coma or even its trajectory slightly. NASA's Juno spacecraft currently orbiting Jupiter could potentially observe 3i Atlas during this flyby, though whether NASA approves a mission extension for this purpose remains uncertain despite Congresswoman Luna's advocacy. Jupiter observations would be valuable for several reasons. First, the comet will be in a different state than during the Mars flyby or the December Earth observations. By March, it will have moved significantly farther from the Sun, and its activity level should have changed accordingly. Second, Jupiter's environment is unique, with powerful radiation and a strong magnetic field that could interact with the comet's coma in observable ways. Third, this represents the last realistic opportunity for spacecraft observations before 3i Atlas exits the solar system. After Jupiter, 3i Atlas heads into the outer solar system and eventually back into interstellar space. He will take it past the orbits of Saturn, Uranus and Neptune over the following years, though the comet will be far too faint for observation by then. Eventually, perhaps a few years from now, 3i Atlas will cross the heliopause, the boundary where the solar wind gives way to the interstellar medium, and become once again an interstellar object travelling through the galaxy. Where it goes from there we'll never know. Perhaps in millions of years it will pass through another star system, providing alien astronomers, if they exist, with the same opportunity we have now. The December observations carry philosophical weight beyond their scientific value. This is humanity's chance to study matter from another star system up close, or as close as we're likely to get in our lifetimes. The comet contains information about stellar and planetary formation processes that occurred billions of years before our Sun existed. Its chemical composition reflects the molecular cloud where it formed, a snapshot of galactic chemistry from an earlier epoch. Every spectrum, every image, every measurement adds to our understanding of how planets and comets form around other stars. But there's also something poignant about the finality of it. 3i Atlas isn't orbiting the Sun. It's not coming back. This is a one-time visit, and when the comet leaves, we lose the opportunity to study it forever. No future mission can chase it down. No technological advancement in our lifetimes will bring it back into range of our instruments. December represents both a culmination and an ending. The peak of observational opportunity followed by a long farewell as the comet fades from our telescopes and returns to the dark stars. The data collected during December will fuel research for years. Cometary scientists will analyze images looking for subtle details in coma structure. Spectroscopists will extract every possible molecule identification from the spectra, building a complete chemical inventory. Dynamicists will refine trajectory calculations, potentially tracing the comet's path backward through the galaxy to estimate where it might have originated. Even if we can't identify a specific home star system, the trajectory tells us from which direction in the galaxy it arrived. Those trajectory calculations are fascinating in their own right. 3I Atlas entered our solar system with a specific velocity and direction. By carefully measuring its path and accounting for gravitational influences from the Sun and planets, astronomers can determine the comet's velocity relative to the local standard of rest, essentially the average motion of stars in our galactic neighbourhood. This velocity vector, combined with the direction from which the comet arrived, provides clues about its origin. Did it come from nearby, perhaps passing through a stellar system just a few light years away? Or has it been travelling through interstellar space for millions of years, crossing vast distances from some distant region of the galaxy? The uncertainties in these calculations are substantial. Small measurement errors in position or velocity compound over the immense timescales and distances involved when tracing trajectories backward. Even tiny gravitational perturbations from passing stars during the comet's interstellar journey would alter its path unpredictably. But the attempt is worthwhile because even rough constraints on origin are scientifically valuable. If nothing else, the trajectory tells us about the density and kinematics of interstellar comets, how many there might be drifting through the galaxy at any given time. Recent studies suggest that interstellar visitors like 3I Atlas might be more common than previously thought. In fact, statistical analyses hint that there's almost always one within our solar system at any given moment, though most are too small or too far from the Sun to be detected. 3I Atlas is visible because it became active, developing a coma that made it much brighter than the inert nucleus alone would be. How many dark, inactive interstellar objects have passed through without detection? We can only estimate based on the few we've found. This realization shifts perspective. Our solar system isn't isolated. The space between planets is traversed continuously by objects from elsewhere in the galaxy. Most pass through unnoticed, dark and cold, but occasionally one comes close enough to the Sun to wake up, to sublimate volatiles and become visible, giving us this precious opportunity to study material from beyond our stellar neighbourhood. 3I Atlas is not an anomaly. It's simply the most recent visitor we've managed to catch and observe thoroughly. December 19th approaches with a sense of urgency in the astronomical community. Proposals for telescope time compete with each other. Researchers juggle schedules to ensure they don't miss observing windows, and data pipelines prepare to handle the influx of observations that will come from instruments around the world and in space. This is what astronomical campaigns look like when the target is fleeting and the stakes are high. For those of us watching from the sidelines, whether as amateur observers capturing our own images, or as interested followers reading about each new discovery, December offers a chance to participate in this moment of cosmic connection. The comet doesn't care that we're watching. It follows its trajectory according to physics that operated before life existed on Earth, and will continue operating after our sun dies. But we care. We look up and see meaning in that fuzzy patch of light, a visitor from the depths of space and time, here for a brief moment before continuing an eternal journey through the galaxy. The December approach is not an ending, not really. It's a transition point, the moment of closest passage before 3I Atlas begins the long retreat into darkness. The data collected will be analysed for years, papers will be written, conferences will debate interpretations, and our understanding of interstellar comets will deepen. But the raw experience of observation, of pointing our telescopes at this visitor and gathering its reflected sunlight photon by photon, that experience peaks in December. It's a moment to treasure, to document, and to remember, because opportunities like this are rare in human lifetimes. The next interstellar comet might not come for years or decades, and when it does, it will be a different object with its own mysteries to unravel. 3I Atlas is unique, and December 2025 is our time with it. The final window before it slips away into the vast dark ocean of space, where it has spent billions of years